Okay, let's unpack this. What if everything we thought we knew about time and space was actually backward? We perceive our reality, this moment right now, as existing in this, well, familiar three-dimensional space, and we're moving forward along just one single line of time. It feels so fundamental, right? It's almost impossible to picture it any other way. But today we're diving into something really groundbreaking, a new theory from Dr. Gunther Kletechka. He's an associate research professor up at the University of Alaska Fairbanks. And he's proposing something pretty radical. It completely flips our understanding of time and, how it relates to space. So our mission for this deep dive is to explore this idea, the idea that time actually has three dimensions, and that time is the fundamental fabric of the universe. In this view, space, our familiar 3D space, it sort of emerges as a secondary effect from that deeper time structure. And here's what makes it so compelling, at least for me. This theory isn't just some abstract concept floating out there. It makes concrete, testable predictions.
Yeah, that's a really key takeaway here. What's fascinating is that this new framework, it offers tangible connections to actual experimental physics. It's aiming to solve some of the biggest, most persistent questions we have in the universe. This isn't just another speculative theory. It's really designed to be put to the test against observable reality.
That is fascinating. Okay, so let's start with the core idea then. For, over a century now, our whole understanding of reality has been built on space-time, right? Three dimensions of space, all tangled up with one single linear dimension of time.
The standard picture.
But Kletechka's theory just completely turns that on its head. He argues for three dimensions of time. He uses this really interesting analogy to help us, wrap our minds around it. He says these three time dimensions are like the primary fabric of everything. Think of the canvas of a painting. And then space, with its familiar three dimensions, is more like the paint on the canvas rather than the canvas itself. That's a pretty profound switch. So if time is the canvas, not just the stage where things happen, what does that fundamentally mean for how we understand reality? Maybe even things like forces or matter.
Well, what really stands out here is that it fundamentally redefines what we think is truly fundamental. If time is the canvas, it implies that time isn't just the backdrop for events. It's the raw material itself, the very essence from which reality springs forth. Yeah. That includes space, matter, forces, everything. So this isn't just a philosophical shift. It suggests that the properties we actually observe in the universe could be direct results, manifestations of this deeper, richer, temporal geometry.
The universe of time. Wow. Okay, that's a huge conceptual leap, especially from our everyday experience. It's one thing to hear three-dimensional time, but how do we even begin to visualize that? Kletechka offers another analogy, this one with paths. So imagine your normal experience of time, just walking down a straight path, always moving forward. That's our familiar first dimension of time. Simple enough.
Right. Linear progression.
Now, picture a second path, but this one crosses the first one sideways, okay? If you could somehow step onto that sideways path while staying in the same moment of regular forward time, you might find yourself in like a slightly different version of the same day. So you could explore alternative outcomes of that moment without actually going backward and forward in the way we usually think. And then the third dimension of time. That's the means to actually transition, to move from one of these outcomes, one possible present, to another.
So it's like a landscape of possibilities.
Yeah, exactly. Like a landscape of possibilities where you can not only move through the present, but also sort of explore potential present side by side. But this sounds like it could really mess with cause and effect, right? That's a big one in physics. How does this theory manage causality with these extra time dimensions?
That's an excellent question. And it's definitely a common hurdle, for many multidimensional time ideas. Some earlier theories really struggled with this. Causality could get murky, and effect might seem to happen before its cause, which is a big problem.
Yeah, that don't work.
Right. But Kletechka's mathematical framework, it's built very rigorously to ensure that causes still precede effects, even within this more complex structure. The theory suggests these extra dimensions, the second and third, they might only really unfold or become apparent under extreme conditions.
Yeah.
Like, think of the very, very early universe, just moments after the Big Bang, or maybe during incredibly high-energy particle collisions, like in our big colliders. Under those extreme energy levels, these normally sort of hidden dimensions could reveal their influence.
Okay, this is where it gets really, really interesting for me. Because this isn't just some cool abstract idea. It makes concrete, testable predictions. And you said it before, but that's what really sets this work apart from a lot of earlier 3D time proposals. Those often stayed purely mathematical, right? Without direct links to things we could actually measure.
Exactly. That's the crucial difference.
So tell us about some of the predictions. What are the most surprising or maybe the most precise things this theory predicts about, well, the fundamental building blocks of our universe? What does it explain that other theories kind of struggle with?
Well, the predictive power is, it's genuinely remarkable. One of the biggest challenges, one of the mysteries in physics has always been why fundamental particles have the specific masses they do. Why does an electron weigh what it weighs, or a quark? Most theories just treat these masses as, well, arbitrary constant numbers we have to measure and plug into the equations.
Just inputs, yeah.
Right. But Klatechka's theory suggests these masses aren't arbitrary at all. They're fundamentally determined by the geometry of these extra time dimensions. It's almost as if the shape of time itself dictates how much intrinsic weight these particles have.
Wow.
For instance, his theory predicts the electron's mass with just astonishing precision. It matches the experimental values we've measured out to 9 decimal places.
9 decimal places.
Nines. And for the top quark, which is much heavier and harder to pin down, the prediction is 173.21 plus or minus 0.51 GeV.
Okay.
And the measured value from experiments is 173.2 plus or minus 0.9 GeV. It's remarkably close. Spot on, really, within the uncertainties.
That's incredible. That level of accuracy, it almost feels like it has to mean something significant, right? It suggests a really deep connection.
It strongly suggests it, yes. It implies there's a profound underlying insight here.
It's almost like these particles aren't just existing in time, but they are expressions of time's structure.
That's a good way to put it. And it goes further. Remember the generation mystery in particle physics?
Oh yeah, why are there 3 families of particles? Like electron, muon, tau, and the quarks too. Why 3?
Exactly. That's been called one of particle physics' deepest puzzles. Why precisely 3 generations, no more, no less? Klatechka's theory shows these 3 generations actually emerge naturally from the temporal structure itself through something called eigenvalue equations.
Okay, eigenvalue equations.
Well,
sounds complex.
It is mathematically, but think of them as fundamental solutions that just pop out naturally from the theory's basic structure, like musical harmonics from a vibrating string. And in this case, these harmonics of time dictate the properties and the family relationships of these particles. So it's not just fitting the data we have, it's an inherent outcome of the math.
So it predicts the existence of 3 generations.
Yes, and it even predicts specific mass ratios between those generations. Plus, it predicts the masses of neutrinos, those incredibly light, ghost-like particles, with really unprecedented precision. That's been another long-standing puzzle. And beyond that, it even forecasts completely new particle resonances, specific energy levels where we should find new particles. Around 2.3 TeV and 4.1 TeV, give or take a bit, things particle colliders can actively search for.
Okay, so that just completely transforms it. It's not just an interesting mathematical idea anymore. It's a physically testable theory with multiple independent ways to check if it's right.
That's what gets physicists really excited, multiple verification channels.
But this leads us to maybe the biggest claim, the most ambitious part of this theory. It could be the key to the grandest of all unresolved physics challenges, unifying quantum mechanics and gravity.
The Holy Grail.
Right. Our best current theories, like the Standard Model, they bring together 3 fundamental forces beautifully: electromagnetism, the strong and weak, nuclear forces, but gravity, Einstein's general relativity. It just doesn't play nice with quantum mechanics.
They break down when you try to combine them.
Exactly. Physicists have been hunting for a theory of everything to unite them for decades. So how does this 3-dimensional time framework step into that huge challenge?
Well, if you connect this to the bigger picture, this framework seems to achieve something truly remarkable. When you try to calculate quantum effects on gravity within this theory, it produces finite, sensible answers. It avoids the nonsensical infinities that pop up and basically break other attempts to unify quantum theory and gravity.
So it gets rid of those mathematical catastrophes.
Exactly. Those infinities are usually a sign that your theory is incomplete or fundamentally flawed at those scales. Klatechka's framework, by its very nature, seems to avoid them. It provides what might be a single coherent mathematical framework capable of describing all forces and particles, unifying them fundamentally through this geometry of time.
And, crucially, again, this isn't just theoretical math. There are real upcoming experiments, tests on the horizon. That's the gold standard, right? So where will we see this theory put to the test in the next few years?
Absolutely. Tests are key. So first, the High Luminosity Large Hadron Collider, the HL-LHC, that's the upgraded LHC, it's expected to have enough energy and data by around 2030 to potentially detect those new particles predicted by the theory, those resonances at 2.3 and 4.1 TeV.
Finding a brand new particle predicted by the theory would be huge.
Monumental. Then there are gravitational waves. The advanced detectors, like LIGO plus PAR, could potentially spot modified signatures in how these waves travel. The theory predicts gravitational waves might travel at a speed slightly different from the speed of light, by a very specific tiny amount, about 1 part in 10 to the 15, and it also predicts extra polarization modes, like different ways the waves can ripple spacetime, things standard relativity doesn't allow.
Wow. Tiny difference, but measurable.
Potentially, yes, with the sensitivity upgrades. And then, looking even broader, at the scale of the whole universe. Major cosmological surveys are coming online. Things like the Euclid space mission, the Vera Rubin Observatory, they'll start getting serious data around 2027. They will test this theory's predictions for dark energy, that mysterious force speeding up the universe's expansion. The theory predicts a specific way dark energy should change over cosmic time, a particular mathematical relationship we can look for in the large-scale structure of the universe.
It sounds like it touches on so many different areas of physics. Does it offer insights into any other long-standing puzzles or anomalies?
It does, actually. There's another intriguing one. The theory seems to naturally explain something from weak interaction parity violation.
Okay, what's that in simple terms?
It's basically a weird asymmetry in nature. The weak nuclear force, one of the fundamental forces, seems to prefer interacting with left-handed particles over right-handed ones. It's like nature's slightly biased in its interactions at the quantum level.
Why?
That's the mystery. But this theory explains this preference purely from the geometry of three-dimensional time. No extra assumptions needed. It just falls out of the structure, which is another sign of its potential deep unifying power.
Okay, so let's bring this back home. What does this all mean for us, for the listener? If this theory or something like it turns out to be right, it would fundamentally rewrite our entire understanding of existence. Instead of time just sort of happening within space, space itself becomes something that emerges from time's deeper three-dimensional structure. Mass, energy, all the forces that govern everything. They would all be just manifestations, different aspects of this underlying 3D temporal geometry. It's truly mind-bending, a complete shift in perspective.
And maybe this raises an important question for you listening right now to consider. If time truly is the fundamental ocean in which reality swings, rather than just being this river we all float down, how might that change our perspective?
On cause and effect, maybe? On possibility. Perhaps even on things like free will. It opens up a lot to think about. It really does. This deep dive has explored a genuinely mind-bending idea. And it's theories like these leaps in thinking that keep pushing the boundaries of what we know, or what we think we know. So if you're as fascinated by these big shifts in scientific thought as we are, we really encourage you to subscribe to the Deep Dive, wherever you get your podcasts. That way you won't miss our next exploration into cutting-edge ideas. And hey, if this discussion sparked a new thought or maybe a burning question for you, please share it. Leave a comment on whatever platform you found this deep dive on. Your engagement, your thoughts, they really help us continue to uncover and discuss the stories that matter most.